Sorry for the slightly delayed start, but we'll get going now. So we're going to continue on with things related to enthalpy and calorimetry today. Before I get into that, since it is Tuesday, I wanted to take a quick look at our homework attempts per week. So this is plotting the average number of homework attempts per student in each week of the semester so far. We're past the halfway point at this time. And what you can see is that last year and this year, there's sort of a downward trend as the semester goes on. There's a dip at spring break. That's what that little dip is. And we are a little bit lower, about 10% lower than what the class last year was. So I guess you guys are less enthralled by the homework assignments than they were a year ago. So far, in the first exam, that didn't seem to matter. Your score was actually a little bit higher on average than last year. We'll see how that translates in the second one. But I will continue to encourage you to do all 4 attempts every week. That is one of the best ways to stay on task in this course. And, you know, like I said, these sort of trends, whether they actually mean anything, it's hard to say at this point, but it does show that our effort has been slowly declining throughout the semester. So we started out the first week around 2.8, 2.9 attempts per student, and we've been as low as like 2.3 recently. So there's a pretty significant drop off, and I think the trend is pretty obvious there. So just an encouragement to try to turn that around a little bit for the rest of the semester. All right, so what we're going to do today is continue on with calorimetry. So last time we introduced what is called a constant pressure calorimeter, which can be as simple as a coffee cup with a thermometer in it. And we talked about how we can use that to measure different things, mainly specific heat capacities of different objects or solids, and also enthalpies of chemical reaction, enthalpy changes. We're going to talk about today a slightly different version, which is called a constant volume calorimeter. And the other word for this that you might see sometimes is called bomb calorimeter, which sounds a lot more violent than it is. This is, I don't want to give the impression that this is something that's like way different than what we've already done. It's just another type of calorimeter. It's a little bit fancier, as this diagram shows. It has more pieces and parts to it. But its main advantage is that it can be used with gases. So the most common application of constant volume calorimetry is to study combustion reactions. Burn something inside of there. You're going to release carbon dioxide and water vapor. So if you're doing that in a constant pressure calorimeter, that carbon dioxide and water vapor will just go everywhere. You'd lose all kinds of heat to the surroundings as a result, and you wouldn't be able to make an accurate measurement. So this contains everything in a sort of tightly sealed container. And this is important sort of in a practical sense for our everyday lives, because this is how they measure the calorie content of food. So when you say this food has this many calories, well, that's just the amount of energy that you release when you burn it or when you digest it. But this is how they would often study that. There's probably better ways to do it now, but you can burn it inside of a calorimeter like this to measure the energy content of food or fuels or anything else you want to burn. Now, there's some advantages of it. The other thing that, technically speaking, because it's constant volume and because you don't then no longer have that P delta V term, you're technically measuring delta E and not delta H. Now, I don't want you to get too hung up on that, though, because in reality, we use those two often interchangeably, and it's perfectly fine to use a constant volume calorimeter to measure an enthalpy change. So don't be fooled by that. It's just that technically speaking, if we're being rigorously true, you don't measure delta H, you measure delta E because you're at constant volume. And we'll get into that in a little bit with the equation that's relevant to that. And the other thing that's nice about these is because everything is so nicely contained and nicely sealed up, it's basically a sealed bucket. It has another little container inside of it where the reaction happens, so that's completely sealed. It's surrounded by water, has a stir to circulate heat, temperature sensors, all kinds of things. So it's, we're not going to get into the details of how this is designed. That's not really important. But the advantage that this also gives us is that the heat capacity of the calorimeter is more precisely known. Because in a coffee cup calorimeter, it's vented, so you're going to always lose some heat to the surroundings. So even if you try to measure that specific heat of the calorimeter, you have some air associated with that. But here, because everything is so well sealed and so well contained, you can get that heat capacity precisely. Because as we talked about last time, when you calculate the heat in a calorimetry situation, there's really 2 terms that goes into that. There's the heat that's absorbed by the water and the heat that's absorbed by the calorimeter. And for this type of calorimeter, that part is much more accurate. But that's just a little bit of background. Now again, why are we measuring delta E instead of delta H? Well, if you remember the definition of delta E, which is Q plus W, and we talked about that if we're at constant pressure, if we just want to approximate what that work is, it can be given as minus P delta V. But in a constant volume calorimeter, delta V equals 0. We're not changing the volume, we're not allowing the gases to expand. So this whole term would be 0 also. So if we measure the heat at constant volume, we just take out this term because the whole thing goes to 0. The heat at constant volume is just directly equal to delta E. Okay, so that's going to be the situation. Although again, we use delta E and delta H interchangeably in most chemistry contexts, so you may very well have a situation in a problem where you're asked to calculate delta H using a constant volume calorimeter, and that doesn't change how you do anything, but technically speaking, it's delta E. And then the equations for the constant volume calorimeter are exactly the same as what we introduced last time, so nothing changes in terms of what you have to do either. So we said that the negative of the heat of reaction is equal to the heat for the calorimeter. So we measure the heat for the calorimeter, and then that's going to be equal and opposite to the heat of the reaction, and that heat for the calorimeter is given by two terms: the mass of water in the calorimeter, the heat capacity of water, and the delta T, plus the overall heat capacity of the calorimeter itself minus water times delta T. So you're going to have one or both of these two terms depending on how the problem is set up, and that doesn't change whether it's constant pressure or constant volume. All the math is the same, so there's nothing different here. So let's give an example then of how we would use this, and like I said, it's not really going to be any different than what we did last time. So if we have a 3.5 gram sample of octane, so octane is one of the major components of gasoline, it has a formula of C8H20, and we burn it in a constant volume calorimeter. Sorry, I think that's the wrong formula. It should be 18. Gosh. What do I know? Nobody called me out on that before. All right. Anyway, 3.545 gram sample of octane. The formula, let's just pretend that's the correct molecular weight. I forget if the molecular weight's wrong now too, but let's just pretend it is. It's burned in a constant volume calorimeter that has a heat capacity of 9.121 kilojoules per Kelvin. If the temperature of the calorimeter rises 17.7 degrees Celsius, what is the combustion enthalpy in kilojoules per mole? So our first step is going to be to calculate the heat for the calorimeter, just like it was before. And that's going to be given by the mass of water, heat capacity of water times delta T, plus the overall heat capacity of the calorimeter times delta T. And again, which of these terms we use depends on what information we have in the problem. The most common mistake people make is they say, oh, 3.45 grams, there's my mass, I'm going to put that into here. But remember that this is the mass of the water in the calorimeter, not the mass of the substance that we're burning or reacting. So that's how much of the octane we're burning, but that's not how much water is there. And if you look closely at this problem, we don't tell you anything about how much water is in the calorimeter. So we're going to ignore that term. Basically, this is one of those problems where we're just going to group everything together into this one term there. All right, so only if we explicitly tell you how much water is in the calorimeter, either the mass directly or the volume, which you can convert to mass using the density, only in that case would we need to consider that term. It's not given here, and often in constant volume calorimetry problems, that's how we do it. We just basically group everything together into one term. So this heat capacity here includes the water that's in the calorimeter, includes all the calorimeter contents, everything else just grouped together into one term. So that's how we're going to do it here, and that makes the math actually somewhat simple. So what we have then is that heat capacity is 9.121 kilojoules per Kelvin or degrees Celsius. Those are equivalent in terms of delta T. And then we're going to multiply that by the delta T. The calorimeter rises 17.7. So if we're burning something, of course, the temperature is going to go up. And that's our delta T, 17.7. And so that tells us then that the heat for the calorimeter is 161.4 kilojoules. Also need to be careful with units because sometimes heat capacities can be in kilojoules or joules. Usually the standard one for water is in joules, so make sure that everything is in the same units if you're going to add it. So here it's going to be kilojoules. That's our only term we have to worry about. And then the next step is the trivial one, which is to say that the heat of reaction is equal to the negative heat for the calorimeter. So you just put a minus sign on that, minus 161.4 kilojoules. But as we also talked about last time, we don't want to stop here. Another common mistake people make is to stop here and just say, oh, there's my delta H, done. But this is the amount of heat that was released for 3.45 grams. This is delta H, but it represents the delta H for 3.45 grams of octane. What we're interested in, and typically this will be the case for any time we're measuring combustion or other types of chemical properties like that, enthalpies, we want kilojoules per mole. So we want to know what is delta H per mole. All right, so that's the issue. This number is delta H, but for 3.45 grams of octane, what is it per mole? So the way we do that, the delta H of, in this case, combustion, when we rate it like that, is the heat of the reaction divided by the moles of the substance that we're burning. So the heat of reaction we just found, but we have to find moles of substance and divide by that. All right, and we know how to find moles now, or if you haven't taken the test yet, learn it in 2 minutes because it's coming up. So we have 3.45 grams. I don't know if my molar mass is off by 2 or not because I had the wrong formula initially, so let's just pretend that that number is correct so I don't have to change my math. And the molar mass is 116.24. So again, assuming there's nothing wrong with the numbers here, which there might be, but let's just go forward with it. That's how many moles that we have. So we're going to divide the delta H that we got for that reaction by the moles of substance to get kilojoules per mole. And so it's a pretty big number. And when the reason that we use things like butane for fuels is because they store a lot of energy. So it's minus 5.42 times 10 to the 30 kilojoules per mole. So that's the delta H when we burn 1 mole of butane, found in this way. Okay, so do we have any questions on that process? Okay, again, pretty much identical to last time. It's a constant volume calorimeter. We're doing a different type of reaction. It's no longer an aqueous reaction. It's a combustion reaction, but the math is the same. All right. The next thing we're going to cover for most of the last part of this chapter 7 is ways that we can actually calculate delta H for a reaction. So calorimetry allows us to measure it. So if we're doing it in a lab, and there very well may be a lab that involves this in general chemistry. Like I said, I never know what's going on over there, and I should. But a lot of times, in a practical setting, it's also nice to be able to just calculate delta H, not to have to measure it every time. And so there are ways of doing that. And so what we're going to talk about today is a way to find delta H for a reaction by combining 2 or more reactions that we already know delta H for. So there's a lot of chemical reactions out there in the world that the delta H is already measured, already tabulated. So sometimes we can combine 2 or more of those to get the delta H for a different reaction that we're interested in. So to do this, we first have to learn how to add together chemical equations. We haven't done that yet. There may have been like a random rogue homework question here or there that kind of asks you to do this in stoichiometry context, but we haven't covered it yet, so now we'll know how to do that correctly. So just like mathematical equations, chemical equations can be added and subtracted. So if you've done systems of equations back in, I guess it would be probably algebra or pre-calc when you guys talk about that stuff, you know how to add together mathematical equations, and you can do the same thing for chemical equations. So let's say we have 2 equations that we want to add together. And we're going to do it very generic to start with. 3a plus 2b going to 4c. And then let's say we have a second equation where 4c plus d goes to 3e. So we want to find what is the combined chemical equation if we carry these 2 out in sequence, or if we add them together. So all you do is you just add the reactants and products together on each side of the arrow. So everything on the left side of the arrow gets added together. Everything on the right side of the arrow gets added together and stays on those respective sides of the arrows. So on the left side, we have 3a plus 2b from the first equation, and then we have 4c plus d from the second equation. So all that's going to go on the left side. And then on the right side, we have 4c plus 3e, the 2 products that would add together then on the right side. So that's how we would combine those 2 equations. Now, when you're doing this, and in the way that we're going to do it for calculating delta H, you have to sort of make sure that this is true. What you're going to often have, or pretty much always will have in the context that we'll use it, is you're going to have something on both sides of the arrow. So we see here that we have 4c over there on the left and 4c on the right. So something that appears on both sides, or something that forms in one equation, 4c formed in equation 1, and then 4c reacted in equation 2, that substance is called an intermediate. So an intermediate is something that forms in one reaction or one step and is consumed in a subsequent one. And so in this example, our C here is the intermediate, or we both have coefficients of force. They have the same coefficient also on both sides. So C is an intermediate, and that means when we're adding together the equations, we can cancel out 4C. Just like if you're adding together algebraic equations, if you had 2x on both sides of the equal sign, they would subtract out from each other. Similar thing here. We have 4C on both sides of the arrow, so they can cancel out. And that means the combined equation, we get rid of the intermediate that appears on both sides, will be written as 3a plus 2b plus d goes to 3e. That 4c appearing on both sides cancels out, for lack of a better word. So that's how we add together equations. Now the trick for us is going to be when we do this in the context of delta H, what's called Hess's Law, using combining equations this way to find delta H. What we have to be able to do also is make sure that we sometimes have to adjust the coefficients in one or more of the given equations to make sure that the intermediates cancel out. So we'll see how that works as well. But once you get the coefficients set correctly, those that appear on both sides of the arrow completely cancel out like they did here for 4C. All right, so let's talk about then the steps for doing this. The first thing is we have to, of course, write out the individual steps. Because what we're working towards is being able to take two given equations and combine them to get another equation that we're interested in, we want to find delta H of. So we're going to write out the individual steps that were given. So let's say in this case it's going to be H2SO4 plus 2NaCl going to 2HCl plus sodium sulfate. So this is actually a cool way to make gaseous HCl in a lab. I wouldn't recommend doing it unless you know what you're doing, because HCl is kind of dangerous to breathe in. But if you drop H2SO4, sulfuric acid, onto salt, sodium chloride, you'll make HCl gas, and then if you breathe that in, your respiratory passages will feel it for a while. All right, so then you have that is the first equation, and then let's say we're going to use HCl to oxidize iron, Fe, into iron chloride and then produce hydrogen in the process. This is our second equation. So if we want to figure out how to add these two equations together to get rid of all intermediates, what we notice is that HCl is formed in the first reaction and consumed in the second reaction. And so if we're trying to add these together to get rid of that intermediate so that it's totally balanced out and we don't have HCl appearing anymore as a reactant or product, we have to adjust the coefficients to ensure that that cancels out. So in situations where we want intermediates to cancel, we have to make sure that the coefficients are the same so that it completely cancels out. If you have different coefficients for something on each side of the arrow, it'll partially cancel out, but if you want it to totally cancel out, you have to adjust the coefficients. So we need to figure out, again, least common multiple, or if you want to formalize the terminology that way, we want this coefficient is a 2 in front of HCl, it's a 6 down here, so we need to adjust one or both of those to make those coefficients the same. Well, if we multiply 2 by 3, we're going to get it to be equal to 6, and that'll have then the same coefficient on both sides of the arrow. So we're going to have to triple this whole thing here. And because it's a balanced equation, whatever we do to HCl, we have to do to all of the reactants and products. We can't just haphazardly put a 6 in front of that and be done, because that's going to unbalance this whole equation. So we have to multiply everything by 3 to keep it balanced. So we're going to adjust those coefficients for this first step here. Now everything's going to be multiplied by 3. So this, of course, by itself is not an equation that's balanced with the smallest possible whole numbers, but then what we can do is add it together with the other one. So this original equation and this modified equation we're going to add together. And when we do that, we're going to have, again, just all the reactants on the left side adding together, all the products on the right side adding together, and then our HCl should cancel out. So we're going to have 2Fe plus 6HCl from this unmodified first equation. And then we're going to have 3H2SO4 and 6NaCl from the second one. And then on the right side of the arrow, we're going to have a bunch of things. We're going to have 2FeCl3, 3H2 from that unmodified equation up here, and then from this we have the 6HCl, and down here in the next line, 3 sodium sulfates. And so now our intermediate HCl has a coefficient of 6 on both sides, so it can be canceled. And so that leaves us with the final equation where we got rid of that intermediate. It's going to be 2Fe, 3H2SO4, 6 sodium chloride to make 2 iron 3 chlorides, hydrogen, and sodium sulfate. All right, so that's going to be the final equation after we've adjusted coefficients to cancel out intermediates and added them together on both sides. All right, so any questions on that process? We'll see it a lot today, so if it's not totally clear now, we'll go through it a few more times. So let's just do an example of that. Just combining the equations before we get into how delta H works. So we have this reagent here, POCl3. It's called phosphorus oxychloride. It's a common reagent in organic synthesis, and it can be prepared in 2 steps. So in the first, you take elemental phosphorus, which has the formula P4, and chlorine gas Cl2. Those combine to give PCl5. In the second step, PCl5 is reacted with water to produce that compound POCl3 and release HCl. So combine the 2 reactions into a single chemical equation, again, making sure that all intermediates cancel out. So what we're going to do first is we're going to write out the 2 equations. Here they're not given to us directly, we have to generate them, so we just have to use the information and make sure they're all balanced. So the first equation, we take phosphorus, which is P4, and chlorine, which is Cl2, to make PCl5. So if we want to balance this with whole numbers, we have 2 chlorines over here. We have 4 phosphoruses over here, so we need to put a 4 there to make sure phosphorus is balanced. And then we have 20 chlorines now, which means this gets a 10. So that's our first step, balanced with smallest whole numbers. And then what we're going to do for the second step is we're going to take that PCl5 and combine it with water. That's what hydrolyzing means, react with water, to make this compound and HCl. And so to balance this one, we have to see what we have going on here. So we're going to have phosphorus is already balanced, oxygen is already balanced. We have 5 chlorines over here, 3 from this one, which means we needed 2 there to balance hydrogen and chlorine. So just 1 coefficient to balance that whole equation. So those are the 2 individual equations. They don't have to be balanced with lowest whole numbers, but that usually makes things easier to go through as you do this. But if you balance them any other way, as long as they're balanced, you'll get to the final answer eventually. So that's what we have, and we have to make sure that our intermediate, which is PCl5, formed as a product in the first reaction, used as a reactant in the second, we have to make sure that cancels out. So it has a coefficient of 4 here, and it has a coefficient of 1 here. So to make sure that this coefficients work out and that they cancel out completely, we're going to have to multiply this whole second equation by 4 to give it the right coefficient. So we're going to have 4 PCl5 plus 4 H2O goes to 4 POCl3 plus 8 HCl. And so now we can add this first equation here unmodified with this modified second equation there. And so when we do this, we're going to start getting good at doing this in our head without having to write everything out in gory detail. What we find is that for this first equation, we have 4 PCl5 as a product. Here we have 4 PCl5 as a reactant. So those will cancel out. We don't have to necessarily write all that out again. And so what we're left with is P4 plus 10 Cl2 from the first equation. Those don't cancel out with anything. And then from this modified second equation, the only reactant that's left is the 4 H2Os. And then on the product side, this product canceled out as an intermediate, and then we're left with the 4 POCl3 and the 8 HCl. And if you do that correctly, those coefficients should already be in their smallest whole number form. They are. There's no way to reduce this any further, and that would be the combined equation getting rid of that PCl5 intermediate. All right, so any questions on that? All right, now the real part of this, why we're learning this in the first place in this part of the course, is to use this process to find delta H. So let's say we had delta H for both of these two equations here. Delta H for the first equation, delta H for the second, and we want to find what delta H is for this combined equation here. We're able to do that if we know how to add the reactions together correctly and if we know some of the key properties of delta H. So let's circle back and talk about that a little bit, some of the properties of delta H that are important. So we've already talked about some of these, but it's going to be important in this context as well. So the sign of delta H we talked about can be positive or negative. That's depending on whether it's endothermic or exothermic. So exothermic is probably more common than endothermic, but both are there. So delta H can be positive or negative. And then the other important thing about delta H is that, how big is delta H? We kind of talked about this a little bit in the context of calorimetry. If you burn a little tiny bit of octane, you're going to have a small delta H. If you burn a huge bucket of it, you're going to have a huge change in enthalpy. So it is dependent on how much substance you have. So delta H is proportional to the amount of substance. And so that means if we adjust the coefficients in a chemical equation, or if we consider the relationship between the number of moles of substance and delta H, they are directly correlated to each other. So let's say we had the decomposition of water into hydrogen and oxygen as elements. So if you wrote it with, in terms of 1 mole of water with coefficient of 1/2 on oxygen, delta H is 286 kilojoules. And we can almost use this as sort of a little add-on with stoichiometry. So what this delta H tells us, this whole thing here is called a thermochemical equation. It has a balanced chemical equation, it has the associated delta H, and what it tells us is that if we produce 1 mole of hydrogen, so this equation is balanced with a coefficient of 1 in front of H2, so it's telling us that the delta H would be exactly that number, 286 kilojoules. So it requires 286 kilojoules of heat when we're going to produce 1 mole of hydrogen. But let's say instead we were going to produce 2 moles of hydrogen. Well, to produce 2 moles of hydrogen, delta H will be double that. We have to double the delta H because there's now, instead of producing 1, we're producing 2 moles. It requires twice as much heat, or 572 kilojoules. So that almost relates to, and it can be related in a lot of ways to stoichiometry. We know that delta H is 286 kilojoules per 1 mole of hydrogen. So if we have a different number of moles of hydrogen, we can find delta H that way, just using that ratio of 286 kilojoules to 1 mole, or any other coefficient in the equation. So that is sort of another property of delta H, is that it scales with how much of the substance we're using in the chemical reaction. All right, so then let's talk about what happens in these two situations. So when we're adding together chemical equations in this part of the course, using what's going to be referred to later on as Hess's Law, what we have to do sometimes is we have to flip an equation to get it to work out, and everything has to get all the intermediates to cancel. So sometimes we have to take the reactants and swap them with the products. So when we do this, let's talk about what happens to delta H. So delta H is, again, products minus reactants. We don't usually calculate it in this way, but that's what it means, is final minus initial, which in a chemical equation is products minus reactants. So if we swap the products and the reactants. If the products become the reactants, the reactants become the products, we just switch the whole direction of the reaction, then we're just going to change the sign of delta H, because now this whole thing is just going to be the opposite of what it was. So when we reverse a reaction, delta H changes sign. So let's say we have this reaction here. So if you take magnesium carbonate and you heat it up, you can make magnesium oxide and release carbon dioxide, and the delta H for this is positive, 117 kilojoules. But let's say we wanted to do the reverse reaction, where we swap the reactants and the products. So we make MgO and CO2 the reactant and combine them. Oops, it's just O. So the products from this become the reactants and vice versa, and that's going to produce MgCO3. So if we're doing this reaction instead, where we've flipped the whole thing over and swapped reactants and products, the delta H is the same in magnitude, just the opposite in sign. It becomes minus 117 kilojoules. Okay, so if we flip the direction of a chemical reaction, we just flip the sign of delta H and nothing else. All right, because sometimes when we're doing this, we might have to take a given equation and flip it to be able to add it together correctly with everything else, as we'll see in a few of the examples today. So that just involves a change in sign of delta H. Now, if we change the coefficients, for two of the examples we did earlier, we had to change the coefficients on one of the equations to get the intermediates to cancel out. When you do that, you just scale delta H by the same amount as the coefficient. So let's say we take this first equation here, the decomposition of magnesium carbonate, and we just double every coefficient. So we make it 2 MgCO3 going to 2 MgO and 2 CO2. If we do that, if we double all the coefficients, we also just double delta H. So delta H would now be 2 times the original delta H, or 234 kilojoules. And then let's say we took that same equation and multiplied everything by 1/2, but we'll put fractional coefficients in front of everything. 1/2 magnesium carbonate going to 1/2 magnesium oxide and 1/2 CO2. So if we do that, we just have to multiply delta H by 1/2. The original delta H is 117. We halved all the coefficients, so we have delta H, 58.5. All right, so that's going to be what happens to delta H if we scale the coefficients in some way. And a lot of times you have to do some combination of these two in these types of problems. You're going to flip the direction and scale the coefficients, in which case both of these would then apply together. You'd flip the sign when you flip the direction, and you would scale the coefficients and you'd scale the delta H if you scale the coefficients. Yes?
So the last example you were talking about, like producing moles of like substance. You do an example of this one.
Yeah, so like in this one here, it's kind of like the relationship between these two equations here. If we heat up magnesium carbonate and produce 1 mole of CO2, it requires 117 kilojoules of heat. Delta H is 117. If we instead wanted to produce 2 moles of CO2, that's corresponds to doubling all the coefficients. That would require 234 kilojoules of heat. So they scale in exactly that same way. All right, any other questions? All right, so then putting this all together with how we're going to actually use it in terms of delta H, this is what's formally called Hess's Law. And so when we add together chemical equations, where we talked about how to do that earlier, now we have to also sometimes scale the coefficients and things, but it turns out that once you're ready to add the two equations together, the delta H's are simply additive. So the math in all of this is pretty simple. You're just going to be, flipping signs, multiplying by small coefficients, and then just adding together at the end. The only tricky part sometimes is getting the equations to add up properly so that you get to the actual equation that you're looking for. So that's the part that we'll have to put a little bit of work into. But once you get the numbers worked out, it's just adding and subtracting. So the total delta H for the reactions you're adding together is just the sum of all the individual ones, however many equations you're adding. Now in this course, 2 or 3 equations is going to be the most common number that we would ask you to combine in this way. Going bigger than that would be kind of tedious in most cases, so it's not going to come up very often. So 2 or 3 equations usually they'd add together. So let's say we had that equation that I gave you earlier. We're going to add these two together now. The first one is this one that we've already seen. And then let's say we did a subsequent reaction that uses the CO2, that's a product here, and is a reactant in the second one. So that's going to combine with hydrogen to make methanol and water. And the delta H for this is minus 131 kilojoules. So if we add these two equations together, as we learned how to do earlier, CO2 is an intermediate. It's formed in the first reaction and it is consumed in the second, so that's going to cancel out. And so our overall equation is going to be MgCO3, the reactant from the first one, 3H2, the reactant from the second, CO2 cancels out, and then on the right side we have MgO plus methanol and water. And the delta H for this is just the sum of the two. So the two given equations that we added together, we just have to add their delta H's to get the overall delta H. So the first one is 117 kilojoules. Second one is minus 131 kilojoules. And that comes out to minus 14 kilojoules. All right, so once we are able to add the two equations together, then we just add the delta H's. So before that, often we're going to have to adjust coefficients, flip one or more of the equations to get them to line up correctly. But once you're ready to add them together, you just add the delta H's, and that's all there is to it. Okay, so any questions on that? Yep.
Well, this is just on the delta H. Will we have to calculate it on our own, or will it be given?
So usually for problems like this, we're going to give you all the delta H values for a set of equations, and then you have to combine those in some way to get delta H for another equation. So there's not really we're going to learn a method towards the end of today on how to actually calculate delta H from even simpler given information, but usually we wouldn't combine those two things together. It'd be one or the other that you're doing. Yeah.
So bringing it all together and making this problem a little trickier, if we had 4 CO2 here and then had to factor the second to make 4 CO2 in that one, we also times the negative 31 by 4.
The negative 131 by 4, and then add them together. All right, you're a little bit ahead of me, but that's where we're going now. Okay, no problem. All right, so now let's see how we actually do that. So let's say so this is the way these problems will be set up. We want to find delta H for this equation here. This is the dimerization of nitrogen dioxide to make N2O4. So we want to find delta H of this, and we're given these two equations, these two thermochemical equations, 2 equations with delta H associated with each of them. So again, that's typically how the information will be given to you. So the first thing we're going to do is figure out how to add these 2 equations together to get this one here. Okay, this is the one that we're interested in finding delta H for. This is our given information. Sometimes to help organize the work a little bit, I like to number the given equations so I don't have to write them out a million times. We'll still end up writing them out at least one more time, but it just helps keep track of them. So we have to figure out what we're going to do here. Now, the way that I like to approach these problems is, okay, this one's not too terrible because we just have one reactant, one product. But you want to find basically situations where a reactant or a product in your equation of interest appears only once in the given equations. In this case, it's pretty straightforward. There's no real choice to be made here. But what we see is that NO2, which is a reactant in this equation, only shows up here in the first given equation. So now we can know what we have to do to this first equation to make sure that we end up with 2 NO2s on the reactant side. So our equation of interest has 2 NO2s as a reactant. This given equation has 1 NO2 as a product. So there's 2 things we have to do to arrange that. We have to flip this equation so that NO2 ends up on the reactant side, and we have to double it to make sure it has a coefficient of 2. So that's equivalent to multiplying the first equation by -2. We're going to flip it, and we're going to double it. So we take this first equation, we flip reactants and products, and we double all the coefficients. So it becomes 2 NO2 going to that 1/2 becomes a 1, I'll leave out the little gas symbols, that they're all gases, it doesn't really matter. And then that O2, we have to double the coefficient to make it a 2. So we're going to flip and double this first equation. That puts 2 NO2s on the reactant side, which is where we want NO2 to be with that coefficient in this unknown equation here. So we did that, and because we did a flipping and a doubling, we're going to have to take that first delta H and multiply it by -2. So the minus sign because we flipped it, and the 2 because we doubled all the coefficients. So that plus 34 becomes a minus 68. All right, and then if we look at what's left, we need to have N2O4, 1 with a coefficient of 1 as the product, and this second equation already has that. It already has 1 N2O4 as a product. All right, and so we're not going to do anything to the second equation, because if we just keep it as is, that's going to leave N2O4 on the product side, and it's going to have the right coefficient already. So for equation 2, we're going to do nothing. We're just going to keep it the same, and that's just going to be N2 plus 2O2 going to N2O4. Because we didn't change anything, delta H is exactly what's given to us, plus 10. So if we did all that analysis correctly, everything should add up now. We're not going to be so cruel to you guys as to give you problems where the equations don't add up correctly. That would be a huge waste of everybody's time. The only thing that you want to sometimes look out for, it's not going to come into play if you're only given 2 equations, obviously, but occasionally, I wouldn't say very often, but occasionally we'll give you extra equations that you don't need. So you'll have to make sure that you're not using extra things that you don't need. And it's good to double check then that everything adds up properly, not just trust yourself to rearrange everything correctly and assume that it's going to work out. So let's check that everything adds up. So what we have here is on the reactant side we have 2 NO2s. From the second equation we have N2 and 2O2, but they're going to cancel out with the N2 plus 2O2 that's up here. So this N2 cancels out because it's on both sides of the arrow. 2O2s cancel out because they're on both sides of the arrow. And then the only product that's left on the right side is N2O4. Okay, so that produced the exact equation we were interested in, the dimerization of NO2. And so now the delta H is just the sum of those two. The modified delta H1 that we got from the first one, and the second delta H, which is plus 10 kilojoules, that was unmodified, and we get minus 58. All right, so that's a relatively straightforward example where we had to combine both of those processes. We had to flip and rearrange equations to make sure that everything, the coefficients all lined up and that the right substances were on the right side of the arrow. And then once we do that, we modify and add the delta H's together. So any questions on that? All right, let's do one with 3 equations. I guess we have a couple of 3 equations here. All right, so this one here is going to be the reaction of carbon with hydrogen to make acetylene. If you've heard of acetylene torches, that has a formula C2H2 that we burn in those torches. And here we're given 3 equations and 3 delta H's. So it's going to be a little bit more complicated, but we're going to follow the same approach. So again, you want to look for substances that only appear once, so this equation that we're interested in has carbon, hydrogen, and C2H2, and you want to find, is there a situation where one of those substances only appears once down here. So C2H2 only appears in the first equation, carbon only appears in the second, and hydrogen only appears in the third, so they all line up that way, so we don't have to make any choices along those lines. So what we're going to do is, in whatever order you want to do it in, make sure that we rearrange these 3 equations to put 2 carbons and 1 hydrogen on the reactant side and 1 C2H2 acetylene on the product side. So whatever order you want to do this in. So we want C2H2 as a product. This first equation here has C2H2 as a reactant, so we're going to flip the first equation. So we're going to flip equation 1. And so this is going to just swap the reactants and products. So it's going to become 2CO2 plus H2O going to C2H2 and 5/2 O2. And for this one, we don't need to change the magnitude of delta H. We don't have to change the coefficients at all because we just want a coefficient of 1 in front of C2H2. But we did have to swap the reactions, and so we're going to change the sign of delta H. So that's going to become, instead of minus 1299.5, it's going to be plus 1299.5. So we switch the sign of the first equation. For equation 2 has carbon in it. We want to have 2 carbons as a reactant. Equation 2 has just 1 carbon as a reactant, so we're going to have to double it to make sure we have a coefficient of 2 in front of C. So we're going to double equation 2. So all these coefficients get doubled, so it's going to be 2 carbon plus 2 O2 going to 2 CO2. And because we doubled it, we have to double the delta H. So minus 393.5 times 2 is minus 787. And then finally what we have to do for equation 3, we want 1 H2 as a reactant. Equation 3 has 1 H2 as a reactant. And so we're going to leave that exactly as is. We don't need to modify anything for that equation. So it's just going to be H2 plus 1/2 O2 goes to H2O, and nothing changes about the delta H. All right, so now we should check to make sure that the equations add up correctly. We made sure that the reactants and products had the right coefficients and were on the right side, so let's also make sure the intermediates cancel out. So from equation 1, we have 2 CO2s, but that's going to cancel out with the 2 CO2s that are over here. So CO2 is on both sides. They are 2 CO2s, and they cancel out. Water appears here as a reactant in equation 1, but it's going to cancel out there as a product. And then what we're left with is we have 2 C's, and there's no carbon on the product side, so that carries through as it should. And then for O2, this is going to be the one that we have to look at a little bit more closely. So O2 appears in all 3 equations. We have to make sure that it completely cancels out because there is no O2 in the overall equation. So we have 2 O2s here, half an O2 there, so 2 plus 1/2 is 2.5. And then over here we have 5/2 O2, which is also 2.5. So O2 does completely cancel out. It's not as straightforward because it appears all 3, but 5/2 on the reactant side, but they cancel out with that 5/2 from the product. So you have to make sure that that works out. And then what we have from here is just H2 is the only reactant left from equation 3, and the only product that hasn't canceled out is C2H2. Okay, so they do add up exactly the way that we want them to. And so now the delta H is just going to be all of those added together. 1299.5 plus minus 787 plus minus 285.8. So all those 3 numbers added together, those 3 there, equals positive 226.7 kilojoules. All right, so again, arranging the equations is usually the tedious and tricky part. Once you have them arranged, the math is pretty simple in these problems. Okay, questions on that? Yeah?
You're essentially just canceling everything out until you get to the end.
Yeah, it's exactly what you're doing. You're canceling it, make sure everything else cancels out until you're left with just 2 carbons and hydrogen on the left side, C2H2 in the product. Everything else cancels out. So it is a little bit like putting a puzzle together. But like I said, we won't give you ones that don't work out. So trust us that the given equations we give you can be added up in some ways. Just once in a while, very, very occasionally, you'll have an extra equation that you don't end up using. So don't assume that you have to use all of them. If you can get to your overall equation by only using, let's say, 2 of the 3, that would be fine. But in here, we had to use all 3. All right, let's do one more example. So this is a more roundabout one. It's the combustion of CO2, but we're using all these weird equations down here that involve strontium oxide, strontium carbonate, and so on. Now in this one here, this is a situation where we're going to follow the same approach, but there's one little thing that's different here. So we're going to number the 3 equations as we always do. And we're going to look at, situations where the reactants and the products only appear once in the given equation. So carbon as a solid only appears over here in equation 3, so that's good. But if we look at O2, we see that O2 is in our overall equation up here as a reactant, but O2 appears both in equation 2 and equation 3. And so what that means is at the start, we're not going to try to balance O2 with a coefficient of 1 in front of it on the reactant side, because there's an infinite number of ways that we can combine equations 2 and equations 3 that give us 1 O2 on the reactant side. So we're not going to know what to do with that at the beginning because it appears 2 times down here. So, do we just need to use equation 2 to balance O2? Do we need to use some combination of equation 2 and equation 3, or just use equation 3? There's all kinds of possibilities that would give us 1 O2 as a reactant, so we're not going to start with that. There's just too many possibilities. There's no way to figure out which one is correct. So we're going to focus on the other ones because carbon, which is here, only appears in equation 3. And then CO2, which is a product up here, only appears in equation 1. So we'll actually start with those two this time. All right, so to get CO2 as a product, here in equation 1 we have CO2 as a reactant. We want it on the product side, so we're going to flip equation 1. And what order you do these in is not important, just to keep track of everything. So I usually try to go in order of 1, 2, 3 and figure out what to do with each of those, but you don't have to do it that way. So we're going to flip equation 1 to put CO2 on the product side, which is where we want it. So this is a very similar reaction to what I showed you earlier with magnesium. This is just strontium instead. And so that puts CO2 on the product side, and so the delta H of this, because we flipped the first equation, is just going to be the negative of that, which is plus 234. We just change the sign. All right, and then from here, as I said, we can't easily balance O2 because it appears in equations 2 and 3, but we have a couple of choices on how to proceed. So one would be, we could go to equation 2 now by recognizing that strontium oxide, which is here in equation 1, also only appears in equation 2. So that needs to cancel out because it's not in our overall equation. There is no strontium species up here. Everything is just carbon, oxygen, CO2. So if we have SRO as a product in this modified equation, it needs to cancel out. And so what we can do then is we can take equation 2 and multiply it by 1/2 to then have the strontium oxide, SRO, canceling out. So if we do 1/2 times equation 2, and again, if you want to do this in this order, or if you want to wait to do this part until the end, that's fine. But if we multiply equation 2 by 1/2, we just take, it's just going to be SRO going to SR and then 1/2 O2. Delta H is going to be 1/2 the second delta H because we multiplied all the coefficients by 1/2. So it's going to be 1184 times 1/2, which is 592 kilojoules. Just that number divided by 2. So we knew we had to do that because we want SRO to cancel out. It doesn't appear in our overall equation. So we know that that's what we have to do to equation 2. Even though it doesn't directly give us the right coefficient for oxygen, it does allow us to cancel that intermediate. And then finally for equation 3, there's a lot of different ways we can look at it. Probably the simplest of those is to say, well, okay, our equation of interest has carbon as a reactant. This one has 2 carbons as a product, so we're going to have to flip it to the other side, and we're going to have to multiply the coefficients by 1/2 to make this a coefficient of 1 instead of 2. So we're going to do minus 1/2 times the third equation, flip it and multiply it by 1/2. So what that ends up with is everything that's on the right side goes to the left, and all the coefficients get cut in half. So it's going to be SR plus C plus 3/2 O2. And then that's going to be our product, again, multiplying everything by 1/2. So it's going to be SrCO3. So delta H for this, we flipped it and halved it, so it's going to be minus 1/2 times the third delta H. So 2440, change the sign, multiply by 1/2, 1220 with a negative. All right, so those are the 3 modified equations. In this case, we had to modify all 3 of them. We had to flip the first, multiply the second by 1/2, flip the third, and multiply by 1/2. Now we can check that everything adds up. So strontium carbonate, which is here, cancels out on the right side of the arrow over there. As we already talked about, strontium oxide cancels out. That's why we arranged equation 2 the way that we did. And then strontium SR here. So what we're left with as reactants are, we have carbon over here, and then oxygen, as we said, was the one that was a little bit weird because it appears in 2 of our given equations. We have 3/2 O2 as a reactant, but then we have 1/2 O2 as a product over here. So that's going to partially cancel out. The 1/2 O2 subtracts from that to leave just 1 net O2. So we have 3/2 O2 on one side, 1/2 O2 on the other side. In net, that's 1 O2. You just subtract the 1/2 O2 from both sides. So that leaves the correct coefficient for O2, and then the only product that's left after all that is CO2. So that got us to the equation we wanted, and then the delta H is just going to be these three numbers added together. 234 plus 592 plus negative 1220 minus 394 kilojoules. All right, so again, that is a terribly inefficient and roundabout way to get delta H for the combustion of carbon to make CO2. But do you want to know if it's correct or not? Well, that's the number we got here, doing it this really weird, convoluted way. We gave that to you up here, same number, minus 394. So it does check out, even though it's a really weird way of getting there. Okay, so this method does work. This is not a particularly effective way of doing it with these weird equations involving strontium, but it did get us where we were going. All right, so any questions on Hess's law? Yeah?
Can you remind me why do you have to flip some of the...
So the reason we flip them is because we need to make sure that the substances that are reactants up here and products end up on the right side of the arrow. So the reason we flipped equation 3 is because in that equation as it's given to us, carbon is on the right side of the arrow. But we want it on the left side for this equation up here, so the way we do that is we flip the whole thing over. And then again, also had to modify the coefficients in that case, but we had to do, flipping it is to make sure that the right reactants and right products are lined up in the final equation. Any other questions? Yeah? Yeah, so the way that oxygen worked is if we wrote the whole thing out, what we would be left with is carbon plus 3/2 O2 goes to CO2 plus 1/2 O2. Basically, there's a 3/2 O2 on the reactant side in this equation, and there's a 1/2 O2 on the product side in this equation. So you have O2 on both sides, so basically it partially cancels out in this case. You can subtract, kind of like we do for algebra. If you had a 3/2 x and a 1/2 x on opposite sides of the equal sign, you'd move one over by subtracting. So we subtract 1/2 O2 from both sides. So that cancels out, and that leaves you with 1 O2 on the reactant side, and that's why it ends up with a coefficient of 1 on the left side of the arrow. So sometimes if you have something on both sides of the arrow, if they don't have the same coefficients on the left and right, it will partially cancel out or subtract out from one side, leaving the rest on the other side. All right, anything else? All right, next thing we're going to cover today is what's called formation equations. This ends up being a more efficient way of getting delta H's for unknown chemical equations. So let's define what a formation equation is first. It's a chemical equation all right, so the name is fairly instructive because it shows the formation of 1 mole of a compound. 1 mole is the important part, or an important part. So it shows the formation of 1 mole of a compound from the elements that make up that compound, the elements in their standard states. We'll get a little bit more about what standard states means here in a second. One thing to keep in mind with formation equations is that fractional coefficients are okay on the reactant side. You're always going to have a coefficient of 1 on the product side because you're showing the formation of 1 mole of a compound, and that's going to be your only product. But on the reactant side, sometimes you need to have fractional coefficients because some of the standard states of elements are, diatomic or polyatomic in some way, like O2, P4. We'll get into those in a little bit. So fractional coefficients are fine on the left side of the equation. You're always going to have just a coefficient of 1 on the right side. So the general form is going to look like this. You're going to have elements on the left side, an arrow, and then on the right side and the product side, you're going to have 1 mole of a compound. The coefficient of 1 won't usually be shown, but it'll be implied. It's just going to be forming 1 mole of a compound. So that's what a formation equation looks like. So to be able to write and recognize formation equations, we do have to talk about a little bit the standard states of elements, because that's what it's always going to be on the reactant side. Elements in their standard state. Well, what does that mean? So the standard state means first the state of matter. Is it a gas, liquid, or solid in its normal? And that would be under like 1 atmosphere of pressure. Like I think it's 298 Kelvin is the standard condition. So whatever the element exists at on Earth at sea level with 25 degrees Celsius temperature. 78 Fahrenheit. So that's what we mean by standard state. So there's a few elements that are gases in their standard state. The obvious ones are the noble gases. We don't call them noble gases for a reason. I mean, we call them that for a reason. They are gases. And then there's a few other non-metal elements that are gases in their standard state. So most of these you're going to be familiar with. So hydrogen, of course, is a gas, and it exists as H2. Nitrogen is a gas. That's most of what the air is that we breathe. Oxygen is another big component of the air we breathe. That's O2. And then two of the halogens, the two lighter halogens, are both diatomic gases. So these are all the elements that are gases. Noble gases would just exist as the element. They're not diatomic. That would just be He, Ne, Xe, and so on for the noble gases. And then these diatomic main group elements are all gases. One of the weird things about the natural world that always fascinates me is that out of all the elements on the periodic table, there's 118 or so at this point. Roughly 20 of those or so are man-made and not, don't exist naturally. But of the 90 or so elements that exist naturally, only 2 of them are liquids. That's always seemed crazy to me. There's only 2 liquids in the whole periodic table. So one of them is Br2. As you go down the halogen series from, fluorine and chlorine are gases, and then you go to Br2, it's a liquid. It's also diatomic. And then, does anybody know the only metal that's a liquid?
Mercury.
Yes, fun to play with in small quantities. All right, so mercury is also a liquid, Hg. And then everything else on the periodic table is a solid. So gases and liquids make up the minority states of matter of all the elements. Everything else is a solid, but there are a few that are also polyatomic, meaning they have, in their standard state, they're made up of molecules that have more than one atom in the formula. So the other halogen, I2, follows the pattern of being diatomic as well. That one being a solid, though. And then there's 3 others that are higher order. So phosphorus is P4. We saw that earlier today. Sulfur and selenium are octanuclear, S8, Se8. So those are the standard states of all the elements. Everything else is just going to be the element by itself. So C for carbon, Fe for iron. There's no, polyatomic nature to any of the other ones except for the ones that I've listed here. All right, so those are what the standard states of all the elements look like. So that's always going to be the reactant in a formation equation. And then the enthalpy change that's associated with that is going to be called the enthalpy of formation. So when you write out a formation equation, the delta H, the enthalpy change that corresponds to that chemical equation, is called the enthalpy of formation. You will often hear this called the heat of formation. So if you hear the term heat of formation, that just means enthalpy of formation. We use those interchangeably. Okay, so the heat of formation, that's the enthalpy change associated with forming 1 mole of a compound from the elements in its standard states. And the abbreviation for this is delta HF, and then you'll have a little circle there that means standard delta H. So whenever you see a little circle on it next to delta H, that means under standard conditions, which you don't have to worry about too much in this class, but that's how it'll be abbreviated. All right, so here's a little thought problem. There's a whole bunch of substances where we can know the delta H of formation already. So if you have an element in its standard state, what is the enthalpy of formation for that element? Is it 0, is it positive or negative, or does it depend? Any guesses? Heard of 0. Anybody else disagree? All right, so 0 is correct. So when you have an element in its standard state, you already know that the delta H formation is 0 for that element. It'll be non-zero for any compound, but it's going to be 0 for the element. The reason is, let's say we're doing the enthalpy of formation for hydrogen gas. Well, a formation equation involves forming the substance from its elements. Well, if we're going to form H2 from H2, there's no net change, right? There's no net reaction if we're forming an element from itself. So that means there's no enthalpy change. So the standard delta H of formation for any standard state element is exactly 0. If the element is not in its standard state, then the enthalpy of formation will not be 0. So if you had hydrogen as just H, which is not the standard state of hydrogen, forming that would involve some sort of enthalpy change. But any element that's in a standard state, it'll be 0. And so in situations where you need all the delta H of formation values to solve the problem, if you see an element in its standard state in the equation, you already know that the delta H formation of that is 0. We don't have to give it to you. You don't have to calculate it in any way. It's just going to be 0. All right, so let's then talk about how to recognize formation equations. That's one thing. So which of the following represents a formation equation? So again, what we're looking for is a situation where we only have 1 mole of compound on the product side, and everything on the reactant side is an element in its standard states. So if we look at choice A here, it does form 1 mole of compound, sodium carbonate, but we see that one of the reactants is not an element. It's another compound. Okay, so this one doesn't work. Actually, both are compounds in this case. So a formation equation would involve forming the compound from its elements. Neither of these is an element. Here what we also have is formation of 1 mole of a compound, and all 3 reactants are elements in their standard state. Sodium solid, carbon solid. The specific form of carbon that's considered standard state is graphite, not diamond. Fortunately, graphite is much more common than diamond. And then 3 halves O2. So again, fractional coefficients are okay, but O2 gas, that's the standard state of oxygen. So this one looks good. All the reactants are elements in their standard states, and the product, there's just 1 mole of a compound. If we look at choice C here, the problem with choice C is that we're forming 2 moles of the compound. All right, so this is basically the formation of 2 moles of compound, but a standard formation equation would only form 1 mole of a compound. This has the smallest whole number coefficients, so it looks nice in that way, but it's not a formation equation because a formation equation only has a coefficient of 1 on the product side. And then finally for choice C, we're forming a compound. That's good, but what we notice here is that oxygen is not in its standard state. Oxygen's standard state is O2. It's one of the diatomic elements. If it's just written as O, it's not in its standard state, and so that would not be part of a formation equation. So choice B is the only one that works. We're again looking for only elements in their standard state on the reactant side. And they have to be in their standard states. So that got rid of choices A and D because A was compounds on the reactant side, D had an element that wasn't in its standard state, and then we're also looking for the formation of 1 mole of a compound as a product. And that got rid of choice C because it was balanced to form 2 moles of that compound. All right, so that's how we recognize formation equations. So there may be some problems like that that just ask you sort of conceptually about what a formation equation is. Now the big deal with formation equations though is that it allows us to calculate delta H for any equation as long as we know the delta H of formation for each reactant and product. So this really is an application of Hess's law. If you write out all the formation equations and you flip them, multiply them, add them together like we just did, you'll get the overall equation, you'll be able to add those together to get delta H, but you don't necessarily have to go through all the effort. If everything that you're given is a formation equation, has a delta HF next to it, we don't have to write out all the equations, add them together, do all that nonsense. We can just use a simple mathematical relationship, which is that the delta H for the reaction that we're interested in is the sum, so that's Greek letter sigma for sum, it's the sum of the delta H's of formation of all of the products minus the sum of the delta H's of formation of all the reactants. So we'll define the terms here a little more clearly. So again, this Greek letter sigma here means sum. You've probably seen that in math courses before. So we're adding up all the delta H's of the products, adding up all the delta H's of the reactants and subtracting the two from each other. And then when we have these little coefficients m and n here, those are the coefficients for each reactant and product, because a formation equation involves forming 1 mole of that compound. So if you have more than 1 mole of that compound on the reactant or product side, you have to multiply the delta H of formation by that coefficient. And again, don't forget that if your reaction has elements involved, the delta H formation for those elements is already 0. You don't have to give those to you or calculate them in any way. All right, but you just have to take all of the delta H formation on the product side, add them together, multiply them by the appropriate coefficients for each one. Same thing on the reactant side, subtract the two to get delta H for the reaction. So you don't have to write everything out. You don't have to do Hess's law. You can just proceed with the numbers right away. So here's an example here. We're going to do the combustion of methane, CH4, natural gas. If we have CH4 and we burn it in O2, we make CO2 and water. We want to know the delta H for this reaction. And we're giving you the delta H as a formation of CH4, which is minus 74.9, CO2, which is minus 393.5, and water gas, which is minus 241.8. So the delta H of formation for the delta H of this reaction in terms of the delta H of formation is going to be the sum of the product side minus the sum on the reactant side. Okay, that equation that we just gave you. So what we have then on the reactant side is we have 1 mole of CH4 with a delta H of formation of minus 74.9. And then the other reactant, we should do products first, sorry. Getting ahead of myself. All right, so we're going to do products minus reactants. So on the product side, we have 1 mole of CO2. The delta H of formation for CO2 is minus 393.5. So that's CO2. We have 2 moles of water, so we have to multiply the delta H of formation of water by 2. So the delta H of formation for water is minus 241.8 kilojoules per mole. So we're going to have to double that for water. And then we're going to subtract from that everything on the reactant side. So for reactant side, we have 1 mole of CH4. Its delta H of formation is minus 74.9. So that's CH4. And then we have 2 moles of O2. What's the delta H of formation for O2 gas? 0, because it's an element in its standard state. It wasn't given to us. And that's just 0. We can just leave it out in reality. So we're going to add those 2 numbers together on the product side, add and then subtract from that number that's on the reactant side. And what we should come up with then is minus 802.2 kilojoules, or somewhere in that vicinity. All right. So if everything that you're given is a delta H of formation, then you can just do products minus reactants, and you'll get delta H for the reaction without having to write out a million equations, without having to balance them and add them and flip them and all that stuff. Okay, so any questions on that? All right, we'll just do one more like that. So we have this reaction that we can use to prepare phosphoric acid. So another form of phosphorus is called red phosphorus. That's just P, it's not P4, so that's not the standard state. But we can combine that with nitric acid, and that'll make phosphoric acid and a couple other byproducts. So what is delta H for this reaction? So the delta H for the reaction is going to be products minus reactants. So on the product side, we have 1 H2O. And the delta H of formation for H2O liquid, this is a different number now because we're forming it as a liquid. The delta H formation depends on whether you're forming solid, liquid, or gas of that compound. So here for the liquid water, it's minus 285.84. So that's water. We have phosphoric acid formed as a product. Sorry, we're at the bottom. So phosphoric acid has a coefficient of 1. Everything should be balanced already. And the delta H formation for phosphoric acid is this big negative number here, minus 1271.7. That's phosphoric acid. And then we have 5 NO2, so we have to multiply its delta H formation by 5. So the delta H formation for NO2 is 33.2. Okay, so that's product side, and then we're going to subtract from that the reactant side. So again, here's where we have to be a little bit careful about the states of the elements. So the standard state for phosphorus is P4, but we don't want to, this is not the same as that, so this is not going to have a delta H of formation of 0. If it was P4, it would be 0, because that's the standard state, but this is a non-standard state of phosphorus. It's called red phosphorus. That's what this picture is showing. And so that's going to have a non-zero delta H, and so we're going to have a coefficient of 1 in front of that, but its delta H formation is minus 17.6. So it has a small enthalpy change associated with forming that from P4, which is the standard state. So that's phosphorus in its non-standard state. Then the other reactant is HNO3. We have 5 of those. And the delta H of formation for HNO3 is minus 173.33. And so that comes out to minus 507.29 kilojoules. All right, so it's just adding and subtracting. You have to be careful with signs and make sure you don't miss the coefficients, but the math is pretty straightforward as far as things that go in this class. All right, questions on that problem or that topic? All right, so on Thursday we'll finish chapter 7 and transition into the next chapter, chapter 8, which is all about gases. And I'll see you guys then. If you have any last minute questions pertaining to your exam, please come find me. I'll have regular office hours today and maybe other times if you need it.